All right, we are doing module number 12 now. So the first thing we start out with is some translations here. Specifically, we are going to do translating the graph of an absolute value function and with 2 steps. Okay, so again, your parent function, y equals the absolute value of x, your translated form y equals absolute value of x minus h plus k. And that moves it h units to the right and k units up. And if h is negative, then it'll move to the left, and you'll see an x plus h in the absolute value bars. If k is negative, it'd be a minus a value, and we would move down. Okay, so an example would be if we have y equals the absolute value of x plus 2 minus 4. Okay, so for our parent function, we would have y equals the absolute value of x, which they're going to give you. That has 1-to-1 slopes on the sides like that. Okay, and then our translation, we are going to move it, since it's x plus 2, that's the same as x minus a negative 2. Okay, so remember that means that we're going to move it left 2. And then since we have the minus 4 in the end, we're going to move it down 4. Okay, so we're going to take that vertex, and we are going to shift it 2 units to the left and 4 units down. Okay, so that would be at negative 2, negative 4. And then what we're going to do is keep that 1-to-1 slope on each side. That won't change at all. Okay, so there is your transformation for one like that. And the 2 steps they mean are left and right or up and down. Okay, so they're not going to do anything crazier than that. All right, let's take a look at your next topic. This is translating the graph of a function in 1 step. So they kind of jump around here a lot with these transformations. They're only going to apply an up, down, or a left, right. So maybe this one they should have had before the one before it, but that's okay. Translating the graph of a function with 1 step. So this is only going to be up or down or left or right. Okay. So if they give you something like y equals f of x, and they want you to graph y equals f of x minus h, that will move it to the right. Okay, if they have y equals f of x plus k, that will move it up. Okay, so it's kind of like what we just said with the absolute value graph, but this will apply to any function. Okay, so you can just take some points on the function and move it accordingly. So some examples that they give in the first one that I'm seeing here. Okay, they have, this is your graph of y equals f of x, and it looks to me like it's just an absolute value one. Okay, and then they also give you y equals g of x, which is a parabola that opens down. Okay, and they give you this point is at 0, 0, and they give you that this point is at 0, 3. Okay, and so what the problem asks you to do is graph y equals f of x plus 4, and also graph y equals g of x minus 3. Okay, so this one, since it's x plus 4, I'm going to move it to the left 4. I'm going to take that 0, 0 and move it to negative 4, 0. Okay. And that's it. You're just going to move it to the left. So don't change the stretch factor or anything else like that, just to the left. Okay. This one is y equals g of x minus 3. That's going to move you down 3. So that 0, 3 will now be at 0, 0. And again, don't change any shape about it. You're just moving it down. Okay? So that's it for that one. They're going to get a little bit repetitive here because I think the next one is in 2 steps. Okay, next we've got translating the graph of a function in 2 steps. Okay, so this is going to be a lot like the absolute value one that we did, but just any function. So they're mostly going to use your parent functions. Okay, so again, if we have an x plus, oops, let's do minus there, x minus h moves to the right. And then at the end, if we have a plus k, that'll move it up. Okay, so in the example that I'm looking at here, they give me y equals square root of x. And they give you the graph of it. Okay, and they give you that point at 0, 0. Okay, and they want you to graph, I'm just going to see how much yeah. It looks to me like maybe you drag it. I'm not really sure how the tools work in Alex for this one. Okay, anyways, they want you to graph y equals the square root of x plus 4. And then outside of the radical, they have plus 2. Okay, so this tells me since it's x plus 4, I'm going to move left 4. And this, at the end, it moves me up 2. Okay, so I'm going to take that 0, 0 and move it left 4 and up 2. So it's at negative 4, 2. And I'll get that same basic shape there. All right, and really I could take any, if I'm not super sure about the shape, I could take any point on that original graph and move it. So some other points would be 1, 1, oops, and 4, 2. So if I wanted more points, I could take all of those points and move them left 3 and up 2. Okay, so again, this one, I'm sorry, left 4. 1, 2, 3, 4, and up 2. I know I'm not super to scale here. Okay, and then the 4, 2, I could move it left 4, which will actually put me at the y-axis, and then up 2. Okay, so move as many points as you want or as you need correctly, and then you'll be good. Okay. Next one, we have just a second here. Let me see. Oh, okay. We have transforming the graph of a function by reflecting over an axis. Okay, it's either your x-axis or your y-axis. Okay, so how that's going to work is if you have y equals f of x, and they want you to graph y equals negative f of x, okay, what that's going to do is flip it, or reflect, I should say, reflect over the y-axis. And if you have y equals f of negative x, that reflects over, oops, I'm sorry, I mixed that up. That's your x-axis for the first one. Okay, this reflects over the y-axis. Okay, so they give us 2 graphs here. the first one they give us is y equals f of x. And it's just a line segment down here. Okay, and then over here they give us y equals g of x, which is kind of a little two segments like that. Okay, in the first one, they want us to graph y equals f of negative x. Okay, so we're going to reflect over the y-axis. So your y-axis is straight up and down. So you want to reflect this line segment over it. So the side that's to the right of the y-axis will now be reflected to the left. Sorry. And then the ones to the left will be to the right. Okay. So we're literally just taking that red segment and like reflecting it. That's it. Okay. For the next one, they want you to do y equals negative g of x. So that's going to be over the x-axis. Okay, so we're going to think of that x-axis as a line of symmetry, like a mirror, and reflection will look something like that. Okay, so just make sure you're paying attention to the notation and just reflecting it correctly there. Okay, next one, we have transforming the graph of a quadratic cubic square root or absolute value function. I feel like you did this in the last module. Seems familiar to me, but that's okay. You will do it again, just in case you need it. Okay. So just remember, again, your parent functions. This is like Algebra 2 deja vu, isn't it? Okay. Your parent function, so we've got quadratic, f of x equals x squared. We have cubic, f of x is x cubed. We have square root, f of x is the square root of x. And we have absolute value, f of x is the absolute value of x. Okay, and then just remember, quick little sketch, quadratic, cubic, come on, square root, and absolute value. Okay, and here's a little hint. They all have the points 0, 0, and 1, 1. Okay, your quadratic and your absolute value also have the point at negative 1, 1. Okay, your cubic has negative 1, negative 1. And then obviously your square root has nothing to the left of it. Okay, so there's some important points on here that we can use. And then just remember, if we do our transformations, f of x would be x minus h squared plus k for your quadratic. For your cubic, x minus h cubed plus k. Absolute value, square root of x minus h plus k. And your absolute value, again. Okay, and h moves right and k moves up. All right, standard for all of them. Okay, so they'll give you your parent graph and they'll ask you to do your transformations on them. Okay, so I'll do an example here. They give you the graph of y equals x cubed, and they want you to graph y equals 2x minus 4 cubed plus 3. Okay, so your graph of y equals x cubed looks like this. Okay, and then like I said above, we have the points at 0, 0. Not to scale very well here, but that's okay. 1, 1, negative 1, 1. Okay, so depending on how you learned it in Algebra 2, I don't know. I always taught my kids to do the horizontal and vertical translations first. So the first thing we're going to do is take that, what we might call the vertex, if it was a parabola here, it's just kind of like the center of the graph, and we are going to move it right 4 because of the x minus 4 and up 3 because of the 3. Okay, so we're going to go right 4 and up 3. Okay, and that's the first step with any of those 4 graphs. You take the point that was at 0, 0 and move it. Okay, now the next step is that stretch factor A. Okay, so that tells you where your point that was at 1, 1 goes. Okay, so that 1, 1, initially, if you move to the, from that 0, 0, you go right 1 and up 1. Okay, now this tells me your stretch factor. If I go right 1, I go up whatever that A value is. Okay, from where that 0, 0 point is. So I'm going to take, where I'm at 4, 3, I'm going to go to the right 1, and I'm going to go up 2. Okay, so right 1 will take me to an x coordinate of 5, and up 2 also takes me to y coordinate of 5. Okay, so I'm going to go, and that will also be standard for every single one of them because they all have the point 1, 1. So that will always get me my 2 points. Okay, it'll get me where the vertex goes, and then it will get me my stretch factor. Now, for the other ones, the other point there that you might need, you can go left 1, okay? Now, for my absolute value in my quadratic, if I go left, I'm going to go up, okay? You can see that if I'm at the vertex and I go left, then I would go up to get to my curve. For my cubic one, go left and then go down. And for my square root one, there's not another point, okay? So since I'm graphing a cubic one, now I'm going to go right 1 and then down 2. So that takes me to 3, 1. And then I have my points that I need to graph my cubic function. Okay? All right. And then be prepared to do it for all of them. The rules apply. Like, it's the same rules no matter what. If this had been like a square root function, then I would have still had the 0.43 and the 0.55. It's just the shape that's different. Okay, or if it had been a quadratic, I'm running out of colors here. Okay, I would have still had the 0.43 and 55, but I would have gone left 1 and up 2. So I would have been at 3, 5, and then I put the shape in. So the steps are really the same. You just add the shape at the end. Okay, and then be careful too. If A is a fraction, you still just move right 1 and up the fraction. Okay, so I could move right 1 and like up a half. Okay, and that would also work. All right. Okay, that's kind of a long one. Remember, we spent like a whole chapter on that in Algebra 2. Okay, our last one for transforming, I think, is writing an equation for a function after a vertical and horizontal translation. So same idea again, but now you have the graph and you give the equation. Another thing you did in Algebra 2. Isn't this fun? Okay. So in this case, they're going to give you a function, and it looks to me they're going to give you a parent function in blue. Okay, and they even tell you they say your parent function is square root of x. Okay, and then they use red to show you the translated function. And there's no stretch factor here. It's just a horizontal or vertical translation. Okay, and they give you this, and they say this is h of x, and they want you to tell what it is. Okay, so you have the grid, so you have enough information to get the coordinates of these points here. I can tell from my grid that this is at -3, 4. And on the blue guy, that's 0, 0. Okay, so that means that I moved left 3, right? And then up 4. Okay, so that means that my h is -3 and my k is 4. So I'm going to have h of x is square root x minus h plus k. Again, since I moved left, h is negative. So x minus a -3 will be +3, and then +4 for the k. And that will be my final answer. Okay. All right, let's move on to the next one. Next one is determining, I missed a syllable. Determining if graphs have symmetry with respect to the x-axis, the y-axis, or the origin. Okay, so just a couple of things here. Okay, if it has symmetry with respect to the x-axis, then your x-axis would be a line of symmetry. Okay, makes sense, right? So your x-axis, this is a graph, roughly, that would have symmetry with respect to the x-axis. Okay, get some graphs here. And the y-axis, these are going to be the easier ones, right? The x-axis and the y-axis. Okay, so one that might have respect to the y-axis, maybe like that. Okay, now the tricky one is the origin, and your hint there is if it has symmetry with respect to both axes, then it has symmetry with respect to the origin. Okay, so let me get a good graph of that. Let me think here for a second. Well, the obvious one, and the one that's going to show up in your problems too, is a circle. Okay, the x-axis is a line of symmetry there, and so is the y-axis. Okay, so this one has symmetry with respect to the origin. Okay. What else do we need here? I think that's good. We'll get some examples, but let me just make sure I'm not leaving anything out. Oh, you know what? Yeah. It would be, I'm missing something there. So let me back up for a second. It's not, yeah. This does have symmetry with respect to the origin, but it's not necessarily that it's both. I'm gonna reword that and give you a better example there. Okay, you would reflect it over one axis and then the other and end up where you started. Here, this one is actually 180-degree rotational symmetry. Okay, so this one would have symmetry with respect to the origin. I could rotate that 180 degrees about the origin. Okay, like almost spin it around. And so the piece that's up on top would then rotate to be the piece that's on the bottom, and it would be the same graph. Okay, you can also think about it as if I can reflect it over X and then Y, if you end up with the same graph. So if I were to reflect this one, or Y and then X, it doesn't really matter. But if I were to take this one and I would first reflect it over the x-axis, so let's see, it would look like that, and then that. Okay, so if I reflect it over the x-axis and then reflect it over the y-axis, so just take that red one and reflect it over the y-axis, and I end up with the same graph. So that means that I have symmetry about the origin. Okay, so we'll look at some examples here. Okay, and they give you a circle, which I kind of already told you about, a parabola, and they give you a sine function. Okay, so for that circle there, we have symmetry. Yes, the x-axis is the line of symmetry. They have like little check marks here. So they ask you to check all of them. So your x-axis is a line of symmetry here. Your y-axis is a line of symmetry here. Okay. Since both are lines of symmetry, it is going to be symmetric over the origin also. Okay. Again, if I think about taking the circle, if I reflect it over the x-axis, the top becomes the bottom becomes the top. And then if I reflect over the y-axis, left becomes right becomes left. It's the same graph. Okay, so all three of them for a circle. For your parabola, the line of symmetry right here, only the y-axis. It's not symmetric over the x-axis or the origin, okay, because I don't have that. If I were to rotate this guy 180 degrees about the origin, then it would be a parabola that opens down. Okay, so we can't rotate it 180 degrees about the origin and stay where we were, okay? The next one, your sine graph here, does not have symmetry over the x-axis, right? If I reflect over the x-axis, I get a different graph. Okay, does not have symmetry over the y-axis. In fact, if I reflected it over the y-axis, I would also have that dashed red line. Okay, but there's a good hint that it actually has the 180-degree rotational symmetry, so the origin. Okay, I always tell my kids, look at it upside down. Do you get the same graph? Okay, and you do with this one, and it's hard. I can't hold my Chromebook upside down because it'll rotate, but just think about if I were to take this blue graph, like think about like a little spinner in a game, and I was to rotate it 180 degrees, I'd have the same graph. So we have that rotational symmetry about the origin. Okay. All right. Next one. Let me see here. Okay. Determine if graphs, evaluating a piecewise defined function. Let me get that one for you. Okay, so piecewise means kind of exactly what it says, that there's different pieces to this function over different intervals for x. So we might have it be 1/4 x plus 1 if x is less than -2. Then we have negative x plus 1 squared plus 2 if x is greater than or equal to -2, but less than or equal to 2. And then it's 2 if x is greater than 2. Okay, so different pieces of the function here. And then they have you evaluate it at different f value or x values. So we want to find g of -3, g of -1, and g of 2. Okay. Well, if we do g of -3, then we're on this piece where x is less than -2. Okay, so g of -3 will be 1/4 -3 plus 1. So we'll have -3/4 plus 1, which is -3/4 plus 4/4, so 1/4. Okay, there's your g of -3. Next, I have g of -1. Okay, so -1 is between -2 and 2. So I would be on this piece right here. I don't know why. Okay, there we go. -1 is between -2 and 2. Okay, so I'll have -1 plus 1 squared plus 2. So that'd be 0 squared. So I just have 0 plus 2, which is 2. Okay, and then for my last piece, g of 2. Now this is tricky, okay? If x is 2, then we're on that second piece, okay, because of the equals 2. Okay, so we're there where x is less than or equal to 2, but still obviously greater than -2. Okay, so now we'll have -2 plus 1 squared, plus 2. So -3 squared plus 2. So we'll have -9 plus 2, which is -7. Okay, all right, let's get another one here. We have finding where a function is increasing, decreasing, or constant given the graph interval notation. Okay, so for this one, we have to determine intervals where the function is strictly increasing, is what it's asking for. Okay, you write a list of intervals and separate each one with a comma. Okay, so let me get the graph here for you. And again, it's on a nice grid, so you'll be able to tell where it changes. But the graph that I'm looking at, oops. Okay, it looks kind of like this. Okay, so they want you to write where the graph is strictly increasing. Okay, so as you move from left to right, where you would be like walking uphill. Okay, so if it's increasing, we're going to see movement like that from left to the right. Decreasing, it will be down. Okay, and constant, it will be flat. Okay, they use interval notation here. Okay, so we would be increasing on my graph. This point is when x is -3, and this point is when x is 1. Okay, and then we have this point is at 5. Oh, no, it's at 4. This point is at 6. This point is at 7. I missed it. This point's at 0. This point's at negative, what do we got, 5. Okay, and it just asks for where it's increasing. So it's increasing on the interval from -3 to 1 because I'm going uphill. Okay, so -3 to 1. They do use curved brackets here. In calculus, we use boxy brackets. Okay, but just do whatever Alex says for this. I don't know if they'll take the box brackets or not, but there you go. And then again, it's increasing on this last little interval there from 6 to 7. Okay, so again, they want you to put your answers separated by commas in the intervals like that. Okay, all right. The next one, we are going to graph a piecewise defined function. And they tell you this is problem type 2. I don't know what problem type 1 is, but there you go. Okay. So we have the function here, f of x is, and it's got 2 pieces to it. It's -x plus 4 if x is less than 1, and it's 2x plus 1 if x is greater than or equal to 1. Okay, and then you also tell if it's continuous. Okay, so let me get this one here first. Okay. So we have 2 linear pieces here, basically. Okay, and you can go ahead and think about like the entire line and then worry about the intervals. So think about just like you're graphing 2 lines here. So the first line that I'm going to graph is y equals -x plus 4. So we're going to have a y-intercept of 4 and a slope of -1. And I tried to do my best to get it on there. Then my other one, I'm going to have y equals 2x plus 1. Okay, so y-intercept of 1 and a slope of 2. Okay, and one thing that I did not show very well is that they both go through this point, this very important point at 1, 3. Okay, so they're both going through there. All right, so now I want to just look at that first one, that -x plus 4 is only if x is less than 1. Okay, so I'm only going to draw the left side of this, and it's x is less than 1. So open circle when x is 1, and then to the left. In fact, I'm going to get a fatter marker here. Okay. Okay, so there's the left piece of it. All right, and then the right piece, And I'm going to be on the yellow one if x is greater than or equal to 1. Okay, so I'm going to fill in my arrow here, but it's also equals to 1. So I'm actually going to have a closed circle right on top of that open circle. Okay, so the purple graph is my final answer. In fact, I'm going to erase the other parts. Oops, I did not want to do that. Okay, so the purple graph, oh boy, this Chromebook is killing me. Okay, whatever. The purple graph is the final answer. All right, just erase it again. But now the question always also asks, is it continuous? And yes, it's continuous because I can go over that graph without picking up my pencil. Okay, an example of one that's not continuous would be if I graphed it and I had, the side with the open circle and then the side with the closed circle did not match up with it. So maybe something like that. We're getting there. Okay, so that one would not be continuous because I can't trace the whole graph without picking up my pencil. Okay, and then just also really make sure that you pay attention to this one would be an open circle, this one would be a closed circle because of the only less than sign in the first one, but the greater than or equal to sign in the second one. Okay, all right, we are in a piecewise defined function. Okay, a couple more left here. Let me see if I can export this drawing and start a new one because it's getting a little glitchy, I think. Okay, give me just a second to make sure it exported right. Looks like it did. I just don't want to have to, okay, I see it now. Okay, I'm gonna clear this drawing. Okay, hopefully that stops with the glitchiness. Okay, the next one, this is kind of an interesting one. This one is going to be finding a difference quotient. I'm actually going to do a new drawing. You can see my kids' drawings here. Okay, let's try this one. Create a difference quotient. There we go. I'm sorry, why did I write create? Finding. I'm all thrown off now. Finding a difference quotient for a linear or quadratic function. And if you ever take a calculus class, you'll be like, oh, I've seen that before. Okay, otherwise this is going to be kind of a weird concept. But your difference quotient is just f of x plus h minus f of x over h. Okay, and you simplify it as much as possible. And there's certain things that will happen for sure when you simplify these. Okay, so as I go through this, I'll show you. But our example that we will use is f of x is 3x squared plus 4x. Okay, and we're supposed to find the difference quotient. So we actually already have part of it, right? We have the f of x that we need. We need to find f of x plus h. Okay, so we're going to evaluate this function, replace your x with x plus h. Okay, so then we'll have 3 We know when we square a quadratic, we'll have x squared plus 2xh plus h squared plus 4x plus 4h, if I distribute that 4. Okay, now I'm going to distribute the 3. All right, and then I also have my 4x plus 4h. Okay, so that's the first thing we need to do is find f of x plus h. Now, some good things happen. F of x plus h minus f of x over h will be f of x plus h Okay, so there is my f of x plus h minus f of x, which is 3x squared plus 4x. And then remember, that's all over h. Okay, well, be really careful that you distribute that negative correctly for your f of x, and we'll have 3x squared plus 6xh plus 3h squared plus 4x plus 4h minus 3x squared minus 4x over h. Okay, now what happens here is when you combine like terms, anything without an h should cancel. Okay, so when I combine my like terms, I see a 3x squared minus 3x squared, and I also see a 4x minus 4x. Nothing else can be combined. Okay, so now I have 6xh plus 3h squared plus 4h over h. Okay, and since every term has an h, I can factor an h out of the numerator and cancel. Okay, so I can write this as h 6x plus 3h plus 4 over h, and then what happens is my h's cancel, and my answer is 6x plus 3h plus 4. And that's your final answer. Okay, and again, these two asterisks every single time. Okay, so once you expand and combine your like terms, anything without an h should have canceled. So if you have anything left that just has x's in it and no h's, you know you made a mistake. Okay, and then that allows you to factor an h out of the numerator and cancel it with the one that's in the denominator. Okay, all right, let's get another one here. We have sum, difference, and product of two functions. All right, so suppose we have the functions f of x equals x minus 6, and g of x is 3x squared. Okay, so now remember, sum means that you're going to add them, product means you're going to multiply them, and difference means you're going to subtract them. Sorry, I skipped over that. Okay, so we are going to find f, and they do kind of like a weird notation here, f plus g of x. It's just f of x plus g of x. Okay, and that's your sum. And then you do f minus g of x. I've never seen it written this way. I don't know why they're doing it this way. I would just write it the second way here. Okay, and that's your difference. And then, and this is especially confusing because there are other ways that we use that dot. Not a big fan, Alex. I would not write it this way. Okay, but that's your product. I would write it the second way on all of those. Okay, so let's start with our sum. F of x plus g of x will be x minus 6 plus 3x squared. That's it. Okay, in general, we would write it with the higher power first, so 3x squared plus x minus 6, but I'm going to guess Alex would take it either way. Okay, when we do our difference, just make sure that you correctly distribute your negative there. So we're going to do f of x minus g of x. So we need to make sure that we do x minus 6 minus 3x squared, or if there's two terms that we distributed it correctly, but otherwise that's it. Oh, and they had me do, now that I look at it, they wanted to do f minus g of 2. Okay. So we could do f of 2 minus g of 2. I didn't even notice they snuck in a number there instead of write these definitions. Did they sneak it in there? Oh, yeah, they did. Okay, sorry. So f of 2 would be 2 minus 6. G of 2 would be 3 times 2 squared. So we would have negative 4 minus 12. So it would be negative 16. Okay. So look for that. I almost missed it, that they wanted you to do it actually at a value for that one. And then they have you find the product, f times g of x. So f of x times g of x. So we will have x minus 6 times 3x squared. And you just distribute it. Okay, so we'll have 3x cubed minus 18x squared. Okay. All right, next one. Quotient of two functions, and they're calling this one basic. Okay, so suppose that we have f of x is negative 5 plus 4x squared, and g of x is 2 minus 9x, and they want us to find f over g of negative 3. Okay, and again, they want you, this means that we're going to do f of negative 3 over g of negative 3. They also tell you values that are not in the domain, so we'll get to that too. Okay. But all we do here is then f of negative 3 would be negative 5 plus 4 times negative 3 squared. So negative 5 plus 4 times 9, which would be negative 5 plus 36, which is 31. Okay. G of negative 3 would be 2 minus 9 times negative 3, which would be 2 minus a negative 27. 2 plus 27 is 29. Okay, so our answer here would be 31 over 29. Okay, values that are not in the domain then, all you need to do is look at your denominator. So the denominator in this case is g of x. And in a rational expression, the denominator can't be 0. So 2 minus 9x cannot be 0. So negative 9x cannot be negative 2. So x cannot be 2/9. Okay? All right. We have 2 more to do. Our next one is expressing a function as a composition of two functions. Okay, so composition, that's when you do like your f of g of x. Okay, and sometimes there's more than one right answer for these, but they tell you you cannot use the identity function. So neither function can just be like f of x equals x. Okay, it's got to be two separate functions, and not the identity one. So suppose h of x is the cube root of 2x squared minus 4. Okay, find two functions, and they use, again, a different notation for this, f of g of x. Okay, which I know they showed it to you that way in Algebra 2. I don't know how much we actually used it like that. Okay, but you got to think about, like, you're plugging one function into another one. Okay, so what you want to kind of think about, what's the outer function? Like, what's the last thing you would do if you were to plug in a value for x? Like, if x were 10 and you plugged it in, right? So you would do 10 squared to get 100, then times 2 to get 200, then subtract 4 to get 196, and then you would cube root it. So the last thing that you would do would be a cube root. Okay? And then inside, you would have the 2x squared minus 4. Okay? So the f is the outer, the g is the inner. Okay, so your outer function is going to be, oops, and I just messed it up, f of x. Come on. Okay, so f of x is the cube root of x. And then your inner function is going to be 2x squared minus 4. Okay, and you can kind of check why that works. F of g of x, then it would be f of 2x squared minus 4, which would be the cube root of 2x squared minus 4. Okay, so you got to kind of think backwards on that. And they're all going to be pretty similar to this. Yeah, I'm looking at them. They're not too crazy. Here's one that's a little bit different. Let me switch colors here. If we have h of x is 4 minus 2x to the fourth, so your outer function would be taking something to the fourth power. So it'd be f of x is x to the fourth. And then your inner function, g of x, would be the 4 minus 2x. So that when you do f of g of x, you do f of 4 minus 2x, which is 4 minus 2x to the fourth. Okay? All right, we got one more left in the video here for Module 12. Another composition one. Okay, so in this one, it's kind of what we just did, but in putting the composition together rather than taking it apart. So this one we have g of x is square root of 2x plus 12, and h of x is x minus 4. Okay, they want you to find g of h, which is g of h of x, and also the domain. Okay, so first of all, g of h, which again is g of h of x. Okay, h of x is x minus 4, so we're doing g of x minus 4, right? Because h of x is x minus 4. Okay, so we're going to take our function g, and wherever I see an x, I'm going to put x minus 4 instead. And And I'll simplify that. So distribute the 2 and combine our like terms. Okay. And then when we come up with the domain, basically anything that ever made a radical negative, so can't square root a negative, or a denominator 0. Okay. In this case, we don't have any denominators here, so we just have to worry about 2x plus 4 has to be greater than or equal to 0. We can square root 0. Okay. So 2x has to be greater than or equal to negative 4. So x has to be greater than or equal to negative 2. Okay. And then remember with your interval notation, negative 2 is our lowest value, which means infinity would be our highest. Square bracket on negative 2, curved bracket on infinity. Okay. So again, there's our answer. And then here's our domain. Okay. Let me just check something quick here. See if I want to do another one. Yeah. Okay. So do one more example that has the rational function in it. Okay. We've got g of x is x plus 6 over x plus 1. H of x is 2x minus 7. Okay. So when we find, let's see, they want us to do g of h in the domain. Okay. So g of h of x would be the same as g of 2x minus 7. Okay. So I'm going to take my g of x, and wherever I see an x, I'm going to replace it with 2x minus 7. So I have 2x minus 7 plus 6 over 2x minus 7 plus 1. So minus 7 plus 6 will be minus 1. Minus 7 plus 1 will be minus 6. Okay, so there's my answer. And then our denominator can't be 0. So 2x can't equal 6. X can't equal 3. Okay, so negative infinity to 3, not including 3, and then 3 to infinity. Okay, and that's the answer that Alex is going to use. In other math classes, they would take a look at g of x also and say that also x can't equal negative 1. But Alex doesn't, you don't have to do that. Okay, so just do what the final answer is. Okay, there you go. There are all your topics in Module 12.